Have you ever wondered about the physics behind certain sports? If physics really is in everything, then it makes sense that it would be seen in athletics as well. In this project, I will analyze a specific sport, in this case football, and figure out the physics behind what makes it work. In football, one of the main aspects of the sport is that the quarterback throws the football to different players to try and score touchdowns. But what allows the quarterback to throw the ball effectively? This is called projectile motion. Projectile motion is seen after the quarterback throws the ball and while the ball is in the air before it is caught. The objectives of this project are to find the different components of a projectile, such as the original velocity, initial velocity in the horizontal and vertical directions, acceleration in the horizontal and vertical directions, the velocities at the max height and top of the football's motion, the max height the football reaches, the velocities upon impact, and the displacement of the football. To find the displacement in the horizontal direction of the football, I looked at where the quarterback threw the football from and where it was caught. Because this was on a football field, I could easily tell where this was. The ball was thrown from 52 yards and caught at 18 yards, so it was thrown a total of 34 yards. By using the conversion factor between yards and meters and multiplying 34 yards by 0.914 meters, I found that the football was thrown a total of 31.076 meters. To find the displacement in the y direction, I assumed that the ball was thrown and caught at the same height. Knowing that both the quarterback and the receiver are 5'11", I was able to convert that to meters by multiplying by 0.305 and got that the ball was thrown and caught at 1.558 meters high. However, since we are looking for displacement and know that the ball was both thrown and caught at the same height, total displacement in the y direction is 0 meters. Now we know that the total horizontal displacement is 31.076 meters and the total vertical displacement is 0 meters. We also know that the time it took for the ball to be thrown and caught is 2.085 seconds based on the video. The next part of this is to find the initial horizontal velocity by using what values we have so far. We are using the formula dx equals the initial velocity multiplied by time plus 1/2 the acceleration multiplied by time squared. We know that horizontal acceleration is 0, so we are left with the equation dx equals vox times t. To solve for the initial horizontal velocity, we divide the horizontal displacement by time. That is 31.076 meters divided by 2.085 seconds. This gives us an initial horizontal velocity of 14.9046 meters per second. Now we need to find the initial vertical velocity, for a football is not thrown completely horizontally, but both horizontally and vertically. To do this, we use the equation ay equals the velocity minus the initial velocity divided by time. We know that the velocity of an angled launch problem is negative, the initial velocity, so we end up with -2 initial velocity on the top divided by time. To solve for the initial velocity, you rearrange the formula to say that the initial velocity equals the acceleration in the y direction multiplied by the time divided by -2. Now all that's left is to plug in the variables, so the acceleration in the y direction is -9.8 meters per second squared multiplied by 2.085 seconds divided by -2. This gives us an initial vertical velocity of 10.2165 meters per second. Now we will work on finding the original angle that the football was thrown at. The angle is crucial because if the football is thrown too high, it won't go to the receiver, and if it is thrown too low, it will hit the other players. To find the angle, set up what you know. We know that the initial horizontal velocity is 14.9046 meters per second, and the initial vertical velocity is 10.2165 meters per second. We also know where the angle is that we are looking for. By using the formula tangent theta equals the opposite side over the adjacent side and plugging in our variables, we can take the inverse tangent of 10.2165 over 14.09046 and find that the angle the ball was initially thrown at is 34.4291 degrees. To find the original velocity now, we start by plugging in all of our givens. So we have the 14.9046 meters per second as our horizontal initial velocity, the 10.2165 meters per second as our vertical initial velocity, and an angle of 34.4291 degrees. By using the formula, initial horizontal velocity equals the original velocity multiplied by cosine of the angle, and plugging in the horizontal variables we are given, we can find that the original velocity the ball was thrown at was 18.07 meters per second. This can also be checked by doing it with the vertical variables and using the formula initial vertical velocity equals the original velocity multiplied by sine of the angle. As seen, we got the same original velocity, 18.07 meters per second. Now we know the original velocity and angle the ball was thrown at, the initial horizontal and vertical velocities, the time, and the total horizontal and vertical displacements. To find the acceleration, draw a free body diagram. When the ball is in the air, the only force acting on it is the force of gravity, which is going down. This means that the only acceleration on this projectile is in the vertical direction. We know that the force of gravity is 9.8 meters per second squared, and since the force is pointing down, that will become a negative 9.8 meters per second squared. Since there are no force vectors pointing anywhere else, there is no horizontal acceleration. This makes the horizontal acceleration 0. To find the velocity when the ball reaches its maximum height, break it down into components. When the ball reaches its maximum height, it is assumed to be horizontal and only have horizontal forces acting on it. This means that the horizontal velocity acting on the ball is still 14.9046 meters per second, and since there are no vertical forces working on the ball, the vertical velocity at this point is 0. This means that the total velocity of the ball at this maximum height is 14.9046 meters per second. Next to find is the maximum height the ball reaches. To do this, plug your variables into the formula, the initial vertical velocity squared divided by -2 multiplied by the vertical acceleration. When variables are plugged in, this gives you a maximum height of 5.325 meters. Now we know the original velocity and angle that the ball was thrown at, the initial horizontal and vertical velocities, the acceleration, the time, the velocities at the projectile's maximum height, the maximum height the projectile reached, and the total horizontal and vertical displacements. The last things to find are the final impact velocities of the ball when the receiver finally catches it. The horizontal velocity has stayed the same throughout the whole motion of the ball, so it stays the same here. As for the vertical velocity, it is the same as the initial vertical velocity, except for that it's now a negative. Once this is found, plug the values into the sides of the triangle that are appropriate and solve for the missing side. Taking the square root of 14.9046 squared plus negative 10.2156 squared gives a final impact velocity of 18.07 meters per second. To find the angle of impact, use the same triangle and solve for the angle using the formula tangent theta equals the opposite side over the adjacent side, and taking the inverse tangent of negative 10.2165 divided by 14.9046. This gives a final angle that the ball was caught at of negative 34.429 degrees. Now we know the original velocity and angle the ball was thrown at, the initial horizontal and vertical velocities, the acceleration, the time, the velocities at the projectile's maximum height the projectile reached, the total horizontal and vertical displacements, and the final impact velocities and angle.